Hey, Greg. Hey, Dave. I'll start in a couple minutes. If you guys have any questions about the global or the local stuff, this will be a good time to ask. You could say it out loud, or you could type it out if it makes it better so everyone hears it. I am recording this, so I will post all of this later. Well, was essentially the biggest or lowest values on the graph. Yes, 100%. That is, yeah, that's exactly global absolute max mins, or what is the, if we can identify the largest value or the smallest value, then what would they be? Versus the local is much more specific to, it's got to be a critical value. If you're going to be a local min or a max, then you have to have been a critical value at some point. Being a critical value also, though, doesn't guarantee that you're a local min or max. But if you were going to be one, you would be one of those. I can get another drink while I'm waiting for you guys. Any other questions? It doesn't have to be about this material. It can be about the upcoming exam or anything like that as well.
I have a question for the min and max again.
Yeah.
Let's say you find the derivative, and then you have x plus 2 equals 0, and then you have x minus 1 equals 0. How would you know, like, when to plug in? Like, you have to plug in a positive number. You know what I mean?
So in that case, you would have two critical values, right? One at
Right.
-1 and -2.
Mm-hmm.
So you need to choose a value that lies in between the two of those, and then to the left and the right of those. Those are the points you want to check. It could be any value. It's just can't be those two values. It's got to be to the sides of them.
Okay. All right. Thanks.
Yep. And then based off of that, which we'll see today, we'll determine whether it's a min or a max or neither. Okay, I think at 2:30, a couple others are going to join in. Let me start sharing my screen with you guys. Good. Hey, Chris, welcome. I'm just seeing this chat piece now. We'll start in a minute, and then we'll go over the second half of this section, the first derivative test and the second derivative test. You guys are all moved out of your dorms now and back at home. That's probably the toughest part for you guys, is having to go back home. All right, it's 2:30, so I'm going to start, and then I'll save this and then share it with the rest of the class for anyone who misses it or comes in late. If you have a question at any point, just type it into the chat. I've got the chat window open, so I'll see the question and then I'll stop it to answer it when it's best to do that. You can definitely come on video or speaking out loud. That's not a problem either. But for question wise, it might be smart to do it through the chat. Yeah, homework 3, I gotta just sit down and grade it. I feel like it's sat in quarantine long enough that there's no virus on it for sure. I just have to find it and then I'm gonna put it in. I just realized, I think it was yesterday, that I haven't graded it yet, so I didn't remember.
Was that homework that we submitted before schools closed?
Yeah, that was the one right before. Yeah,
Okay.
that very last one. So some of you submitted it online. See, look at that. The world has changed so much since that last class. Very disappointed that I was right about it. I thought I was crazy. And I wish I had been. Let's see here. All right, so let's start with I'm going to review real quick on the critical number piece. I had a good question today from someone about the critical number, and it's a common misunderstanding, so I want to make sure that we're aware of it. So the critical number, definition of a critical number is when you take the derivative of a function and set it equal to 0, the value that makes that derivative 0 is a critical number. Also, any value that makes the derivative undefined is considered to be a critical number, as long as it existed in the original function. If you meet either one of those criteria, that's a critical number. The thing to remember about a critical number is that's its only definition. It does not imply more, and students often think that it does. A critical number, for example, does not imply that you're a local min or a max. It doesn't. But if you were a local min or a max, you would be a critical number. So there are critical numbers that aren't local mins or maxes, but every local min or max is a critical number. See that little difference there? It's kind of like the whole square is a rectangle, but not all rectangles are squares type piece. And so that's the thing with critical numbers. We know that if you're going to be a local min or max, the first place we're going to look for you is as a critical number, because you'd have to be one of those if you exist.
And for it to be a local max or min, you do the derivative tests, yes?
Yes, so then that's what we'll go over today. Specifically, how do we find out whether a critical number is a local max or min? The other thing to be aware of is, and it's so funny, it's crazy, because I mean, at least for myself, I have struggled with this concept many times, especially every time I teach it. I have to remind myself often. Global min or max, the global or absolute max or min is such an easy concept. It's got to be the biggest number or the smallest number, yet it is such a hard thing and a problem that we still all get wrong because of the fine little details in there. And so one thing to be aware of, if you're a global min or max, you don't have to be a critical number at all. You can be a global min or max and not be a critical number, because critical numbers are describing a hump in some type of curve, right? You're going up a hill and now you've got to be going down it, because we're saying it happens when the derivative is equal to 0. Right, when you can draw a horizontal line as a tangent. So that's got to be at these hills or at these valleys, right? If you drew it underneath it. That's what critical numbers are searching for. But global maxes or mins don't have to occur only at those locations. I mean, depending on the function that we're talking about, it may not be continuous. What if it's a completely discontinuous function? There's no continuity anywhere in it, like just the set of integers plotted against itself. 1, 1, 2, 2, 3, 3, 4, 4. And if you were to limit that domain, there would be a maximum and there would be a minimum. And those will be global maxes or mins, but not necessarily local maxes or mins, because local maxes or mins are very, very specific, and they do involve more on continuity and the ability to draw something around it and contain points that still exist, which you wouldn't be able to do for a single point. But if you had 3 points or a set of points, you'd be able to at least do that type of thing. So global maxes or mins, because they're not always occurring at a critical value, they could occur there. They definitely could occur at a critical value. But because they don't always occur there, then the next question is, well, how do we know if one exists if we don't have a graph? If we don't have a graph, how do we know that it exists? The only places they could exist are critical values and at the endpoints. It's something you should think about. Why is that the case, that they can only occur at those two spots? But if you have a closed set, so a closed domain where the endpoints are included, you could have a max or a min definitely happening there. And if it doesn't happen there and it does exist, then it's going to have to be at a critical value. That's where it would need to be. If you have an open set where the endpoints aren't included, your global max or min can't occur at the endpoints because the endpoints aren't included. And you wouldn't be able to list the very next point right next to that endpoint because of the whole rational, irrational continuum stuff. Every number you pick, I'll find one closer. So if it's an open set, you can't have global max or min anywhere but at a critical value. And if it's a closed set, you can have global maxes or mins occurring at the endpoints.
So how would you know that you have a global max or min when it's an open domain, and how would you know what they are?
So let's take a look at an example. I'll do it on here. One where it's closed and open, and it's an easy one for us. Let's just do x squared. So f of x is equal to x squared. On its normal domain, this has no global max. The only thing it's got is a global min at 0, and it also has a local min at 0, and no local maxes at all. But let's restrict this domain. Let's restrict it to -2 is less than or equal to x less than or equal to 2. Less than 2. So this is going to be a little bit different. So notice the difference here. Notice this fine detail. This is an half open, half closed set. The left side is closed. We're including the endpoint -2. The right side is open, and it does not include it, right? So 2 is not a part of this domain. Now the question is, what are all the local maxes and mins? What are all the global maxes or mins? So to find the local min, it's gotta occur in a spot where we can draw a circle around it to include some points that exist near it. And in that little set, in that little circle you draw, that location is the lowest point of that location, of that circle, inside that circle. And that's the first derivative test. We're going to see that in a couple minutes, is going to really give us a system for testing that out. But it's got to be at a critical value. And the critical values occur from the derivative of this function. So the derivative of this function is 2x. And so we ask ourselves, when does 2x equal 0? And the only time where that happens is that x is equal to 0. So x equals 0 is a critical value of f. Add that as a note. So x equals 0 is a critical value of f. Now that may or may not tell us That doesn't tell us whether it's a local min or max, but it tells us that if there is one, it's got to occur here at x equals 0. It can't occur anywhere else. That's what the theorems tell us. So we're going to do the first derivative test in a couple minutes to test that out. Now we visually see this. We know that this is a local minimum. We can see it. But we're going to see algebraically how we can test that. Back to now, what about the global max or the mins given this restricted domain? Okay, there is a global max. So there's a global max, global absolute. I actually use absolute usually more than global. So there's an absolute max at x is equal to -2. And the reason it's the absolute max, when you plug -2 into this function, you get +4 out. +4 is the largest value you can get out given this restricted domain. We can visually see that. It's the largest value. So that is what makes it the global max. It happened at an endpoint. That is not a critical value. Notice that there is not another global max at x is equal to +2. And the reason is because +2 is not included as part of this answer. It's not part of the domain. So you can't plug it. I mean, we know that if we plug 2 in, it would be 4, but 2 is not, by restriction here, not a part of this. So there is not a global max at x is equal to +2. If I was to, I'm going to just for a second change this. If I was to change this problem to -2, x is greater than -2 and less than +2. So this is completely an open domain now, where the endpoints are not included. The next question, and this is an important concept that you need to understand, there is no global max. Even though we've got these points and we can say no value coming out will ever be greater than 4, for sure, there is no global max because you can't identify it. And that's a hard idea to wrap your mind. I mean, it's something that people make mistakes on for sure. So think about that. This is an open set. We do not have a global max value. And I challenge you to think about I mean, if you don't believe it, like if it doesn't seem reasonable that, I mean, we can visually see this. It doesn't go greater than 4. Why isn't there some maximum that we can state? We'll come up with what is it? Where is that at? You need to be able to say at x is equal to this is where that global max occurs. And you can't do that. If you say, okay, well, I'm going to try. All right, state x, it's going to happen at x is equal to 1.99. But I'm going to say, well, there's another value in between 1.99 and 2, 1.999. So you give me a closer one, 1.9 followed by 99 nines. Well, I'm going to say 1.9 followed by 199 nines. So no matter what you can do, you can't lock down that location. And if you can't lock down that location, it is not a global absolute max. That's the best way of thinking about this. So if there was going to be some other global max in this function, it would have to then occur at a critical value. And in this case, there is not an absolute max. There is an absolute min. So in both the unrestricted and the restricted, in both the open and the closed domains, there is, as a fact, a global min. And as at x is equal to 0. Happens to also be the local min, local max as well. And it happens to be a critical value and not an endpoint. So don't overread what some of these things tell you. That's really the thing you should be focusing in on. I think the process is rather easy because all you're doing is taking derivatives. That's not new. I mean, it's new to last chapter, but it's not new information now. You're not learning how to take a new type of derivative. You're learning how to take the derivative and use the information it gives us to infer things about this function. So that's what you should be focusing in on, the details of that. All right, so now let's use the first derivative test to go ahead and figure out how we can use, so how does the first derivative test tell us whether something is a local max or a local min? Let me see if it makes sense in the way that they write it. So if p is a critical number of a continuous function that is differentiable near p, so if you can take the derivative of f at p, then f and p is a critical number. Then f has a relative maximum at p if and only if there's a sign change from positive to negative. And okay, yeah, we should do this by example. So here we've got our example right here. We'll do some more complicated ones after this one. So the first derivative test says, take your critical value that you found from the first derivative and use that as a way of dividing up the screen, the domain. Let me see if I can graphically do this for you. I know there's a whiteboard, so let's try that out. So we're using the f of x is equal to x squared. Its derivative is 2x. The critical value is at 0. And now what we're doing is applying the first derivative test. You draw a number line for the first derivative test. Doing this with a mouse, so I apologize. All right. And you put your critical values on the number line. There's 0. That's our critical value. So C, I'm sorry, this is terrible. CV. And now what you need to do is pick a value that is not 0. 2. One to the left of it, one to the right of it. Pick numbers that are easy to work with. Maybe a really large negative number, maybe a really small negative number, who knows? We're working with 2x, so this is an easy one. It doesn't really matter. So I'm going to pick negative 10. Actually, I'm going to pick negative 1 since I got to draw this. And positive 1. Those are two values that aren't 0, that are to the left and the right of it. And now I plug them. This is the important thing. This is where students make mistakes. I plug these values into the first derivative. I plug them into the first derivative, not into the original function. And I'm going to look at what the signs are. Let's talk it out loud since I can't bounce back and forth. I'll come, Alita, I'll give you, I just saw your question. I'll answer that in a second. So our derivative is 2x. So when I plug negative 1 into 2x, that is a negative number, negative 2. So I make a note, negative. When I plug positive 1 into the derivative 2x, 2 times 1 is positive 2, so it's a positive. I have 0 concern about what the number is and only its sign. That's the only thing I'm concerned about. So attention to detail on the number is not important. The only thing you need to pay attention to are the signs and what's the ending result. So the first derivative test says that if you do this process that we just did, which was to take the critical value, plot it on a number line. If there's multiple ones, then you plot multiple ones on there. And in between each region that these critical values create, pick a number that's in between them and test them by plugging them back into the first derivative. And based off of the sign, they give us information. And so here I see a negative and a positive surrounding this 0 critical value. And so what that tells me is that the slope was going down and now it's going up at 0. And so since it was going down, since it was negative and now it's positive, we have found a minimum. So when you go from negative to positive, you found a local minimum. That's it. That's what you found. That's what the first derivative test gives us. If it goes from so imagine if it was going from positive to negative, it's giving us a local max. That's it. So first derivative test, very easy. I mean, it's a matter of just calculating derivative, setting it equal to 0, down. We'll do another example just to see it where there's a couple different critical values. To answer Alita's question, so are these boundaries given? This is a great question on that. So no, it depends really. So like if I said, given f of x is equal to x squared, find all local maxes and mins, and I mentioned nothing about the domain, you need to assume it will be whatever its natural domain is. What does x squared normally let in, and what does it normally give out? So the domain would be all real numbers. I could totally say, hey, given f of x is equal to x squared, and x is greater than or equal to -2 and less than 2 as its domain, now what are those local maxes or mins? But it will be obvious. It's either mentioned or it's not mentioned at all. And if it's not mentioned at all, the assumption is that this is something like there. That is something that you should be able to figure out if it's not mentioned. That's the type of function. All right. Let's do another first derivative test, and then we'll do second derivative, and that's the info for today. All right, so let's look at. And we're gonna, this is the best part, having Desmos and all this stuff available to us, we can see these answers before we even perform this stuff. And that's what you should be doing. I mean, if this was in person, you had a graphing calculator, I'd be telling you the same thing. Plot the function on your graphing calculator, look at what the answers should be, so that you know that your work makes sense at the end. So we'll figure out what the answers are before we even do these tests, and then we'll take a look from there. So let's see, x squared plus x. I want 2 pumps, so I'm going to need to have at least a cubic. So x to the third plus x squared. I'll make that a little bit bigger. There we go, 2x squared. And that's perfect. We're going to have we've got a local max right here. So this is...
Professor, it's still on the page with the number line.
Yeah, it's still the whiteboard.
Thank you. I totally did not know that. All right. Good. All right. So here's x to the third plus 2x squared. What we've got here, so given its normal domain, I'm not listing any specific domain, there is no global max or min, right? Because if we head towards negative infinity, this function's just going to get smaller and smaller. There is no global max because if we go towards the right, towards positive infinity, it's just going to get larger and larger. So then the only thing left we've got are local mins and maxes. And we've got them. We can see a local min and the max right here. Here's a local max, right? Draw a circle around this. There's inside that small little domain that you create when you draw around it, there's a maximum value. Same thing here, draw a circle around this. There's going to be a local minimum right there. This one's easy. It looks like it's 0. This one, not as much. Like we can click on it, 1.33. Okay, so I mean, we can tell what that one is, but you can't always tell. So if we have a graph, we visually see it, how do we know where these exact max and mins are? So prior to calculus, the only thing you had was if you were working with quadratics, you had the whole x is equal to negative b over 2a, and that told you where a vertex existed. That rule only works for quadratics. And so anything beyond quadratics, which is everything else, you had no tools. Now you've got the first derivative test as a way of finding those max and mins. So our derivative here, g of x, is 3x squared plus 4x. We can rewrite that by factoring, so we can factor out an x, so g of x is equal to x times 3x plus 4. And so that means x is equal to 0. That's where the one critical value is at. And x is equal to negative 4/3 when you solve this for 0. So there's the two those are your two critical values. Now we already see, hey, this is definitely a max and a min. We can see it because we're looking at it. But if you didn't have a graphing calculator, if you didn't have Desmos, how do you know that these are truly maxes or mins? And how do you know which one is which? You could technically plug these into the original function, and then you'll know which one's bigger and which one's smaller, and you can make an assumption that one's a max and one's a min, but you won't always be right. So the first derivative test is what we're going to need to do here. So I'm going to go back to the whiteboard. I'm going to take this 3x squared plus 4x. That's our first derivative. Actually, I'll use this version of it. This is the better version. And I'll take our two critical values, and then we'll perform the critical value test. All right. Clear. Clear. All right, so we had 0 and negative 4/3. So 0's over here, and then negative 4/3. This is terrible. All right. And our function is g of x equals 3x squared plus, oh, it's
Four.
x times, sorry, I'm going to actually change that to x times 3x plus 4, like that. Right, so it's in the factored form. It makes it easier for figuring out your signs. So the numbers now that we've got to, drawing, good, okay. So we've got to pick some numbers and pick the easiest numbers possible. So for example, something left of negative 4/3, negative 1,000. Sometimes a really large number will help with your calculations to make them faster. Number in between negative 4/3 and 0, negative 1. It's an easy number to work with. And then to the right of 0, 1,000. Sorry. All right, so when we plug in negative 1,000, this is why picking big numbers is going to be easy. Negative 1,000 is a negative number. Negative 1,000 times 3 is a negative number, plus 4 is still a negative number. Means we have negative times a negative, which is a positive. So numbers chosen on this side of the graph are going to have positive slopes. In between negative 4/3 and 0, we pick negative 1. So here we get a negative number times, now because it's a small number, we've got to do the math. Negative 1 times 3 is negative 3. Negative 3 plus 4 is a positive number. Negative times a positive is a negative number. So we've got a positive and now a negative. And then when we plug in positive 1,000, we get a positive times a positive. Positive. And positive times positive is a positive number. So we go from positive to negative. So we're going up and then down. So we have a maximum at negative 4/3. And then we're going from negative slope to positive slope at 0, which means we have a local minimum at 0. So if we go back to Desmos, we can confirm that we had a max at, see, we have a max at negative 4/3, and we have a minimum here at 0. Because think about it. If you're looking at this graph, what is first derivative test doing? It's saying we have identified these humps. And then we're looking at the values in between to see if we were increasing and then decreasing or decreasing and then increasing. So it makes makes a lot of sense that this is exactly what it would give us. That's your first derivative test. Let's take a look, not at the second derivative test yet. And the book actually does, I think the book skips over this. I'm not sure why it does that. But here's a question to think about. What if you were to take what if you tried to apply the first derivative test to the first derivative? Like, does that give us something that's informative? And the answer is, yeah, it does. We can use the first derivative test on the first derivative, treating the first derivative like it was the function itself. And then the information that the second derivative, the real second derivative, but using the first derivative test, will give us are possible points of inflection. So it starts to tell us information about the concavity of a curve, because just because something is increasing doesn't tell you anything about concavity. We could have things that are increasing that have downward concavity. You know, here's one, this part of x squared. right? Make sure I'm showing you this screen right now. Yeah, good. Yeah, so like this part right here. See, here's an increasing function. It's got positive slope, but it's got downward, it's got up, it has an up concavity. But here, over on this part right here, you've got an increasing function, but it's got downward concavity. So the first derivative test doesn't give us any information about that, but the second derivative, not the second derivative test, but the second derivative using the concept of the first derivative test will give us that. I'm going to share over to you now, over to Word document. I'm going to type up this, what I'm just saying, because I know it's confusing. So let's try this out.
How did you get a negative when you plug in -1 times 3 plus 4?
So because it was -1 times 3, so that's -3, and then plus 4. -3 plus 4 is +1.
Right, and then so how'd you get like concave down and then up?
Oh, I didn't get concave down or up from that. I only got the local min or max.
Oh, okay.
Yeah. So I'm going to show you now how to do that. So if we have f of x is equal to x squared and we want to think about its concavity, we know to the left of 0, actually it's got positive concavity everywhere, right? So its derivative, f prime, is equal to 2x, and its second derivative is equal to 2. This derivative, because it's just 2, is always positive. Therefore, f has positive concavity across its domain and no point of inflection. It's a fact, right? This is always positive, bam. If this was always negative, same thing, except it would be negative concavity. Let's look at the other example that we are working on in Desmo. So x cubed plus 2x squared. So I'll let this one be g this time. So let g of x equal x cubed plus 2x squared. So its derivative is 3x squared plus 4x. And its second derivative is 6x plus 4. All right, so the first derivative, we saw that it has critical values when g prime of x is equal to 0. So at x is equal to 0 and -4/3, right? When we did the first, after completing the first derivative test, we saw that so after completing the first derivative test, we saw that there was a max, a local max at x equals -4/3 and a local min at x equals 0. So those are things that we saw from, that's what we took from the first derivative test. If we apply the first derivative test to g prime of x, so what that means is we take the derivative of g prime and get the second derivative and set the second derivative equal to 0. all right? What we see here, we find possible, put that in bold, possible points of inflection at G prime, G double prime, right? So if you're going to be a point of inflection, you're going to happen at this location, but it only gives us a possible one. Just like the critical values only gave us a possible local min or max. This is a possible point of inflection, but if it has to happen somewhere, it's going to be here. And what you do is the same exact process that you did for the first derivative test. You do that for this, and it will tell you if it is a point of inflection. How? If it changes sign. So here, let's find our possible points of inflection. We call them PPIs. So if we have our PPIs here are when 6x plus 4 is equal to 0, right? That specifically is at x is equal to negative 2/3, right? Because you bring the 4 over, divide by 6. So if there's going to be a point of inflection, it happens at x is equal to negative 2/3. And the way we test that is with that whole number line. So put your negative 2/3 on that number line. Let's use dash instead of under. So this way. So you got your number line. You're going to need to pick a number that is to the left of positive 2/3. Oh, sorry, negative 2/3. So a number that is left of negative 2/3, which would be, pick a really big number, so negative 1,000. I'll put it in parentheses so we know that that's just a choice. A number to the right of 2/3, you could do a really large positive number here. 0 might also be advantageous. 0 is always an easy number to work with. And so when I plug those numbers into the second derivative, so just like the first derivative, you plug it into the one that gave you those values out. So when I plug this number in, negative 1,000, I get negative 6,000 plus 4, so that's going to be a negative number. So when x is less than negative 2/3, our f of x's are less than 0. They're negative. They are negative. When x is greater than negative 2/3, so let's say 0. 6 times 0 is 0, positive 4. They're going to be positive. So then f of x is greater than 0. They are positive. So when x is less than negative 2/3, the way we read this, since they're negative, then we have negative concavity. Or downward, it's downward concave. And this is therefore positive concavity. This is not the second derivative test. This is the first derivative test being applied to the first derivative. So that's what this is telling us. And it tells us what the concavity is. Now, if you go from negative to positive concavity or positive to negative concavity, that location where that happens, which in this case is negative 2/3, is a point of inflection. That's the definition of a point of inflection. The location where you switch concavities from one to the other. And that's why this was a possible point of inflection, but now we know that this is a point of inflection. So x equals negative 2/3 is a point of inflection. And it's a point of inflection because we changed from negative to positive, or positive to negative.
So critical numbers are basically points of inflection if they're a maximum or minimum.
The critical number of a first derivative. Say your question again.
So basically, if it goes from negative to positive or positive to negative, then it's automatically a point of inflection.
Definitely, yes. That's the definition of point of inflection.
Got it.
Yeah, and if that's going to exist, it's going to have to be true for this. it would, that value would definitely make GW double prime of X 0. So don't get, these aren't critical values. They're critical values of first derivatives, but we'd never call them that. This is just, we call them possible points of inflection, so we don't get confused. Critical values are when you set the first derivative equal to 0 only, or when it doesn't exist, the first derivative.
So first derivative, critical numbers, second derivative, points of inflection.
Possible points of inflection, yes. Yeah. All right, so then we got, so now what is, the big question is, what is the actual second derivative test? So the first derivative test and the second derivative test are designed to find local max and mins. So the second derivative test is the method of using the second derivative to find a local min or max. You may say to yourself, why would you do that? If you had to take the first derivative, why didn't you stop there? Imagine that you're just working on a problem where you've got to find the concavity, you got to do a full workup on an actual function. So you're going to need to know local max and mins, you're going to need to know the concavity of these curves. You're going to do the second derivative no matter what. So wouldn't it be nice if the second derivative, if you have to take the first derivative, but imagine you don't have to take the first derivative test. You just take the first derivative, and jump to the second derivative, and use that information. And that's what the second derivative test does. So the second derivative test says, if you know the critical values, which you found from the first derivative, so if you have the critical values, you can plug them into the second derivative and it may give you information. Doesn't always, but it might. And so if you have the critical values, if you have the critical values of a function f, then the following is true. If f double prime of, so I'm going to use C as the critical value, right? So if f double prime of that critical value is greater than 0, then you have found a local minimum. It's actually opposite of what you may think. So if it's greater than 0, we've now found a minimum. And if it is less than 0, then you have found a local max. I'm going to confirm. We know that there's a local minimum at 0 here, so let's confirm that that's true. Actually, no, this is the x cubed one, so let's confirm it for this one. This one here would be inconclusive. Actually, no, it would be positive. Yeah. So then you found a local minimum. Right, you found a local minimum, which we did. So notice this second derivative test here, f double prime of x is equal to 2. It's always positive. So when you plug in any critical values, critical value is 0. When you plug 0 in, you get a positive number out, which is greater than 0. Then that means you have found a local minimum. Second derivative test works. Notice it's a little bit quicker. If we didn't do the first derivative test, all we did was take the first derivative. We say, okay, critical value is at 0. Bam. Take the second derivative, you get f double prime of x is equal to 2. You plug in your critical value, it's positive. Now you know that's a local minimum. You didn't have to draw a line. You didn't have to pick 2 points. You didn't have to test them out. There's an argument to be made that that's a little bit faster. If we look at this one here, g of x is equal to x cubed plus 2x squared. Let's add, oh, here's the second derivative. That's 6x plus 4. Second derivative test says, and this is where it gets confusing. We take the critical values that we found in the first derivative test. Those are the numbers that we're plugging into g double prime. We're not putting it on a number line. It's not the first derivative test again. We're not picking 2 random points, to the left and right of something that made something 0. We're not doing that. This is specifically take your critical values, plug them into the second derivative test, and look at the sign. If it's positive or negative, we get information. So I'll do that down here below all the other stuff we already did. So we had one critical value. No, we have two at 0 and -4/3. I'm going to plug those two critical values into the second derivative. So 0 is a critical value. 0 times 6x plus 4 is equal to 4. That's a positive number. Therefore, since it's positive, at x equals 0, we must have a local min. And what did our stuff say here? Up here, do we get a concavity? So local max at -4/3, local min at x is equal to 0. Yeah, local min confirms it's what we already know. I'm going to plug the other critical value in, -4/3. And now when I do -4/3, so -4/3 times 6, the 3 and the 6 become 2. So it's -2 times 4. So that's -8. -8 plus 4 is a -4. This time it's a negative number. And since it's negative, at x is equal to -4/3, we must have a local max. And both are true. We saw that with the first derivative test. First derivative test would have been fine here. But if this problem said do the full workup, find the concavity, you don't have to do the first derivative test at all. You find the critical values by using the first derivative, and then you go immediately to the second derivative. The one thing that I have not mentioned yet that needs to be mentioned here is, so this is when you plug the critical value into the second derivative, you get greater than or less than 0. What happens if it's equal to 0? And so that's important to be aware of that case. So if we have f double prime of c, of that critical value, if it comes out as 0, then we must use the first derivative test to see if it's local. It's just not conclusive. So if f double prime of c is equal to 0, we don't have enough information. Second derivative test cannot be employed for that specific critical value. You may have gotten information about the other ones, but for that one, you're going to need to definitely use the first derivative test then to see how it works. You know, whether it's a max or min, or neither, All right, let's go back to the book. This is a good time if you have any specific questions at this point. You may want, this might be a good time. I'm just going to see if there's a problem that we can do from the book to go over this, but that's the first derivative test and the second derivative test. So it states it. So here, let's look at an example. That's too similar to the one that we just did. Let's try another one. Here's a good one. This is a great one because it involves a trig function, so it's not just the straightforward polynomials. So consider the family of functions given by h of x equals x squared plus cosine of kx, where k is some positive real number. Use the graphing utility to sketch the graph. The axis, fine. Explain why the graph of h has no inflection points. Oh wait, no, this is outside of the second piece. All right, let's go back to, let's do sine of x. Sine of x is a good one. We know what the graph of this looks like. We can answer all of these questions ahead of time. So this is a really good function to work with. So you've got f of x is equal to sine of x. And what we want to do here is we want to find its max and mins, which we know exactly where they occur at. They occur at pi over 2 and at 3 pi over 2. right? At the top of your unit circle and at the bottom. But we're going to see that the first derivative test gives us that information, and we'll see what the second derivative test gives us, and we'll look at the concavity as well and see how they work in this type of scenario. So I'll go back to Word. So this is our graph. We know that it's got to happen at pi over 2. So let me just highlight that, right? So pi over 2, you've got your max at x is equal to 3 pi over 2. The bottom of your unit circle, you've got your min. Those have to be critical values. Maybe there's more critical values, but these are definitely the locations where this happens at. And we'll restrict the domain. Let me switch you over to Word. All right, blank page. All right, so we're starting with, so f of x is equal to sine of x. And we'll restrict the domain because the domain's too big. So let's make x be in, we'll do a closed one so that the endpoints are possibilities. Let's say 0 through 2 pi. The goal here is to find out x global, all global, and local max mins. So both of those. Talk about concavity on the domain. I think it's the full workup of this function. So we start by just taking derivatives. Let's get f prime. F prime of x is equal to cosine of x. Right? And we want to find the critical values. So the first step is take derivative. If we do this as steps, 1, take derivative. Take first. 2, set first derivative equal to 0. Solve for x. So so cosine of x is equal to 0. Therefore, x is equal to, so remember, cosine measures the horizontal distances to the vertical axis. And so that happens at pi over 2 and 3 pi over 2. So at pi over 2 and 3 pi over 2, and 3 pi over 2. All right, so at those two locations, cosine is equal to 0. If you don't know that, you test it on your calculator. I mean, you should at least be aware that it's got to happen at 0, pi over 2, pi, 3 pi over 2, one of those 4 locations. So it happens there. It does not happen at 0 or 2 pi in this case. All right, so cosine of 0, that's equal to 0. So set the first derivative equal to 0 and solve for x. We get our x's there. So let's use this to, actually, let's skip this. Let's go right to the second derivative test because this is a full workup and that's what you should do in a normal situation. We've got our critical values. So set equal to 0 and solve for x to find the critical values. And in this case, these are your critical values. So now we're going to take the second derivative. Take the second derivative. And so when we do that, we get f double prime x is equal to, now derivative of cosine is negative sine of x. There we go. All right. So that's your second derivative. Let's talk concavity. Let's not go into the second derivative test yet. So to do concavity, we go and talk about then set the second derivative. Similar process to the first. Set the second derivative equal to 0 and find possible, this is to find possible points of inflection. Possible ones. And so negative sine of x is equal to 0. That implies right, that implies that sine of x is equal to 0, right? If you just divide both sides. And when does that happen? Therefore, that happens, sine of 0 is your horizontal distance to the vertical, your vertical distance to the horizontal axis. That happens at the 3 o'clock and at the 9 o'clock positions. So at angle 0 and at angle pi. So that's when sine and negative sine of x are equal to 0. Those are possible points of inflection. We can go ahead and now run the test on that. So pick a number to the left of 0, -1. It's got to be in the domain. Actually, but this is a restricted domain. Possible points of inflection. Technically speaking, inside this domain, it can't be a point of 0, can't be a point of inflection because it can't be changing from something to another thing because there's nothing to the left of it. In terms of this is a wave function and it's continuous over the entire domain, we know that there is something to the, technically speaking, to the left of it. And so you have to pay attention to what the domain is. We can't have 0 is the smallest number that we can have to the left. So there is no arrow here, right? Like a 0, that's the end point. So then you're going to have to pick a number in between 0 and pi. Pi over 2 is in between there. And again, the same, now you can pick a number between pi and 2 pi because pi is not an endpoint. And so a number in between pi and 2 pi would be 3 pi over 2. And then finally we get to 2 pi, which is the end of our domain. We know this is the end of our domain because we defined it. It's right up here. It says 0 to 2 pi, and those are all included. So using the first derivative test or the second derivative test here, it changes our number line a little bit. So the numbers we picked to test are these right here. This is testing for concavity. We plug them back into f double prime. All right, so pi over 2. We want to see what their signs are. All right, when I plug pi over 2 into f double prime, which is sine of x, normal sine of pi over 2 is +1. But this is negative, not sine of x, so it would be -1. And that means we have negative concavity. So there is negative concavity between 0 and 3 pi over 2. Sorry, not 3 pi over 2, between 0 and pi. So we have negative concavity when x is in the interval from 0 to pi. We'll confirm that. We'll go back to the image in a little bit. Maybe you have it up, and we'll see that that's true. We plug in the other value, the other possible point of inflection that we found, which is we're not plugging that in, sorry, I apologize. The number in between those two. So we pick 3 pi over 2, that's between pi and the end of our domain of 2 pi. So f double prime of pi, 3 pi over 2. Now when we plug 3 pi over 2 in, normally sine of 3 pi over 2 is -1, but this is negative sign, so that means negative and negative is a +1. And so that means in the interval, we have positive concavity when x is in the interval of pi to 2 pi. That would be the positive concavity interval. That was not the second derivative test. It was using a version of the first derivative test, but taking second derivative information. Now we're going to use the second derivative test, right, to see what we get here. So now, employ the second derivative test using the critical values found in the first derivative. So we plug those values this time into the second derivative. So again, f double prime and our critical values, we see them listed here. So critical values are those right there. I already plugged those in. They happen to be the numbers I picked. That was by chance, actually. All right, so we've already tested these numbers out. These happen to be the critical values as well. And we already know what the signs are. Very lucky choices that I made. It would have worked if I picked any other number. I didn't realize I was picking those. So the second derivative test tells us, I'm just going to copy this and put it over here because you still have to go through the same process. Right, and then this, you plug your critical values in, and it tells me that at x is equal to, so at x is equal to pi over 2, that's a negative number. Second derivative test tells me that because it's a negative number, therefore there's a local max there, local max here. And at x is equal to 3 pi over 2, since it's positive, therefore local min. Local min here. So in this case, I happened to use the critical values because they fell within those boundaries. So I killed 2 birds with 1 stone. I didn't have to do 4 calculations. I was able to use it all as one. So that's really useful. And so this is telling me that I've got negative concavity from 0 to pi, and then so we're going from negative to positive concavity, and there's a local max at pi over 2 and at 3 pi over 2. Let's go back to the graph in Desmos and make sure that that's true. So let's restrict it to just the domain we're working with. So 0 is less than or equal to x is less than or equal to 2 pi. That's what we're looking for. And my results said that we had negative concavity from 0 to pi. 0 to pi. That's negative concavity. From pi to 3 pi over 2, we have positive concavity. So that's confirmed. And the second derivative test says that at pi over 2 and at 3 pi over 2, we have our specific max and mins. At pi over 2, it said it was a maximum. And at 3 pi over 2, it said it's a minimum. We already drew pi over 2 and 3 pi over 2 out. We knew where they were going to be. But it's confirming. And that, yeah, this is a maximum. And yes, this is a minimum. So that's what I've got for you. And I'm pretty happy that it took literally an hour. And that's what I want to try and only keep it to an hour. That's your first derivative test. That's your second derivative test. It seems very straightforward. It is. The derivatives, those things that you've already done. This is why when people say calculus is easier than pre-calc and stuff, you've done the hard work. The derivatives, that was the hard stuff so far. This stuff, I mean, this is easy. This is just, you have to know about the existence of these theories and how to use them. But the process involved in these calculations is nothing more than what you've been doing in algebra. So you've got to just know that these things exist and how we can take this information and apply it. So that's your first and your second derivative test, plus the second derivative concavity portion using critical values, which we find from that first derivative, and that it tells us about these local mins and maxes. And then the only other additional piece of info that you learn in this section is that global concept of global maxes and mins. You guys have, let's see, The short quiz at the end of the week, will it be on this concept? Yes. Yeah, the short quiz at the end of the week will be on this concept. What did I say? I was gonna put that up. Oh, I haven't put it up yet. I have so many classes that I'm trying to keep up with here.
Was there something due tonight?
There is a quiz due tonight, but that is just your chapter 2 quiz.
Right.
Right. So chapter 2 quiz on the derivatives 2.1 through 2.5, that's due tonight.
Okay.
Did I say that there was an end of the week? I think I did say that there's an end of the week like homework grade quiz. Let me just see. Oh, I think it's under a module. I think it's actually in the assignment itself. Week 1. Now, whatever I wrote, that's what I'm going to stick to. So let me see. State. There will be a summary quiz of multiple sections in 2 weeks. Okay, that one. At the end of the week, you will complete a short quiz, which will count towards homework. Yeah, it's going to be a short quiz. It counts towards your homework grade. And it is going to be focused on just the things that we went over today. Do you understand these most basic concepts? I'm not looking to put difficult functions on there. I'm looking to make sure you really know what it means to be a local min or max. Do you really know what critical values are? Can you find them? Something very short and easy, something that just by doing this, reading this, the resources I've given you, trying the problems out, that just from doing that alone is all you need for this quiz. And it counts towards homework. So it's not going towards the actual, you'll have a real quiz on this material like you normally would have had if we were meeting face to face. But these small little ones, this is the only way I can make sure that people are showing up for class and in an online scenario, because you don't want to save this to the end and just be like, forget what happens. It's not even intentional. It just life happens and then things get delayed. And sometimes things only get, they get delayed because people aren't pushing you. So this is it's a small push to make sure that you're staying on top of stuff at a pace that would be reasonable. What will be like how the quiz was. It could be like the online quiz today. I think that so far the grades have been amazing on those. Hopefully it's not. Hopefully people aren't cheating, and it's just you guys really understand what's going on. But definitely the end of the week quiz will be a short, small thing like this, and the future quizzes will get more detail. Let me, just because I'm sure everyone doesn't want to stay for too long on this. My recommendation coming up, so next Wednesday is when the midterm will be. It's on my to-do list. That's the last thing on my to-do list for today is to be working on your midterm, trying to figure out what I'm going to do and all that other stuff. Again, if any of your other professors have talked to you about what they're doing for midterms, I'm very curious to know what they're doing. And if you want to share that with me, email it to me or put it up in the discussion board. I would really like to know. But next Monday, we'll have a review for the midterm. Nothing's changed on that end. I want to be able to make sure that I provide an opportunity where I'm there to answer whatever questions you've got for that.
So the midterm's not Monday.
No, I'm going to have it Wednesday so that we can, I don't know, did I list, if I listed it as Monday, I'm going to do Wednesday. Because we can.
Perfect, because I already have 2 exams that day.
All right, perfect. Yeah, so let's do.
Yeah, because like the way they're doing it now for online, like my chem professor for our test, she's giving us a document that we print out and then we send a PDF of it to her with all the work that we did on it. While with my bio exam, they're basically doing it like how you do your quizzes, where it's through Canvas.
And mine is going to be, I don't see the problem. I would love to do the print part, but I don't want to assume that everyone can print it. And I also don't want to assume that all of you can take good pictures. So where you're taking a picture that I can actually read and then grade. So it definitely is going to involve some type of interactive part. But, I don't know if there might be a project portion of it. I just don't know.
Okay.
I'm not looking to kill you guys with work for sure. I'm definitely trying to take into consideration the situation. But my most important thing is that we're being honest about what we know and that we're not cheating to get this grade, because it just doesn't help in the long run. And it also proves that we can't do this type of stuff. I mean, if this is a terrible failure because everyone cheats, Montclair in the future may make the decision that they're just closing school, and that you lose the semester altogether and you get your money back. But this is a new world that we may have to consider, that this type of shit happens. I don't know. We don't know what this new world is yet. None of us do. So we have to see, is this a one-time thing or not? But I'd say, you know, all of us should be doing our best and being honest as possible on this type of stuff. So, but I have to keep that in mind too, that not everyone is going to be honest. So I try to design it the best way possible, prevent cheating, but I'm not perfect for sure.
And are there still going to be group assignments in the future?
I believe there is going to be that. So there, in the past, there's always been this one group project that supposedly is a very good group project, one on biology and fetuses or something, fetal growth. I am leaning, I have to really read through it. I am leaning towards that still existing, because it's a good, because you would have done that outside of class anyway, and you don't have to physically be together to do it ever. You set up Zoom in some way. You know, you can do it. You guys have options. You definitely have ways of communicating with each other. So I think we're going to probably stick with that. Yeah, the only thing I could say, the biggest changes, we lost a whole week. We lost 2 full classes, so we're going to not cover as much information as we would have normally. But at most, that's probably 2 sections, and that won't be a big deal. That won't be a big deal at all. Do you guys have other questions? So on Monday, I will do a review though. So come with whatever questions you've got. No, I think, so is there a specific time on Wednesday for the exam? I don't think so. I mean, I get that some of your other professors aren't. I have a lot of experience. I've been teaching online since 2006. And so one of my best practices is I don't assume people can show up at the same time for anything. I mean, best case scenario is that you only have a technical problem, and that's the reason. And the worst case scenario is because life is crazy right now, and you know, we're online, so we need to pretend like, you know, we don't need to pretend like we're in face to face. That's why showing up for this is totally up to you. Will not hold it against you. I will see if I'm able to get a list of students who did log in, so that I'll give you attendance credit. But I'm not going to take away attendance credit. I'm not going to mark anyone as absent. It just makes you know, you look, you know, you get a sticker for being here today, you know. But it's impressive, you know, that you showed up. Yeah, so there will definitely, the only thing I would do is, I believe that I should have access to you within a 24-hour time period. So that's why, you know, if I created a quiz today and said, hey, this should be due by, today's Wednesday, so it would be reasonable to expect that it would be due by Friday, you know, that type of thing. I wouldn't give a quiz, I wouldn't put out a quiz tonight and just automatically say, hey, it's due the very next midnight. I definitely want a little bit more than 24-hour warning, but everyone should be getting your emails. I'm being very consistent on how I post this information. So if you're having problems with that, also let me know, so I can help you technically on that side of it. Any other questions?
Oh, sorry. Are there going to be a lot of questions on the midterms so they're not weighted super heavy?
I will put more than I do on the quizzes. I'm sure the quizzes must frustrate some of you because they are worth a lot of points than, you know, each question. But I don't want to put too many either. Don't want to be able to keep it down to a reasonable amount of time. So I would imagine it will not be nearly as long as the midterm would have been if we met face to face, because that would have been a full period. This last quiz, probably, technically speaking, was probably only a 20-minute quiz at most. I could see this being an hour long. And that's the thing, I want to just, you know, technical issues and all that other stuff, I will always give a little additional window, which is what I did with this quiz. This quiz, I think I made 35 minutes, I think. It's not a 35-minute quiz. But I don't want the time to be an issue. So, you know, this will be at most an hour and a half. When you start it, you will have to work it through the entire time. But beyond that, yeah, it is what it is. This is a crazy time. I'm not, you know, it'll be a midterm, but it isn't going to be anything crazy. You should study for it. I have a unique way of being able to still know whether you know the information or not. So, but it's also not going to be one of those, you know, in-person paper ones where they tend to be a little bit more challenging than something like this. Other questions?
For the last example you gave, where the domain was 0 to 2 pi, is the
Mhm.
global min 0 and the global max is 2 pi?
Let me go back to the graph real quick. It's from 0 to 2 pi. There was a global, no, neither one were global maxes or mins actually for 0 to 2 pi. Global max and mins occurred at pi over 2 and 3 pi over 2. Remember what we're talking about. We're just talking about the largest point that could come out of the sine wave. And on that domain is 1. And the lowest one was -1. And so that's that would be the global max and min, and the local max and min, both occurring at critical values and not at the endpoints at all.
So what would determine if the global max and min is critical values instead of the endpoints?
Good question. Excellent. Actually, yeah. So this makes sense. Yeah, what you're saying makes sense. So what you need to do, we're looking at the picture, so we know. But what you would need to do then is, after you've got the critical values and you know that they are local maxes and mins, plug them into F, into the original function, to see what are the outputs. Then plug the endpoints of the domain into the original function and see what those outputs are. And then from there, you can see whether or not which one's going to be the global max or the min. And I'm just, oh no, my mouse is frozen. My mouse did this yesterday too. I don't know what happens. Give me a second. I may lose you guys. If I do, I'll come back in, but my mouse is frozen, and the trick I've got to do sometimes makes me